Uh, Thanks for joining this section. So we have three wonderful talks. The first speaker is Yiting. Yiting is a tenure-track faculty at Max Planck Institute for Informatics, where she leads the network and the cloud system research group. She got her PhD degree from computer science from Rice University. And before joining MPI, she was a research scientist at Facebook. Let's welcome Yiting.
Okay, thanks. Well, thanks for the introduction. Yeah, so today I'll share our latest work. It is an open framework for enabling system innovation of optical data center network. And this is exactly in the same topic as George Papen, and he said it's not very practical to build a system in the switch, and we hold a different opinion. This talk is about how to build such a system on the switch. Okay, so I'll skip the background. So the traffic keeps growing in the data center, and we also need to consider some operational goals. And with the slowdown of Moore's law for electrical switches, it is hard to achieve all these performance and operational goals using electrical switches. So that's why people, the networking community has shifted attention to optical data center networks. And optical data center networks use optical switches. As everyone knows, they are circuit switches, and they are bufferless without queuing delay, but you need to buffer packets elsewhere in your network, either on the host or on the switches. Yeah, and over the past 15 years, a bunch of optical data center network architectures have been proposed. Because of their power efficiency, low cost, low latency, and high bandwidth, and also changeable network topology. But unfortunately, we find the system work on top of these optical hardware quite lagging. We think this is because it is a closed ecosystem, because every optical data center network architecture is essentially a closed ecosystem with specialized optical hardware and customized software stack on top. And the evaluation is usually based on some homegrown simulation and small scale testbed. So this makes the systems research for optical data center network quite siloed. And this is because it's tied to the underlying hardware, and there's a lack of a unified platform for implementation and evaluation. So our work is to decouple the software and hardware to enable them to evolve independently. So how should we do that? We built a general optical framework, and it can support different optical data center network architectures on top. We call it the open flow for optical data center networks. So we come up with a very simple abstraction and a user API, which I'll show later. And this is transparent to cloud applications. Like cloud users don't need to know what fabric your application is actually running on, like either the traditional electrical-based data center network or an optical data center network. Okay, and we can have support different hardware architectures on top in a plug and play manner. And you can also support some emulated fabric, like using programmable switches if the researchers don't own the optical hardware. And later, as your optical fabric evolves, say you want to have some newer optical technology tested out, you don't need to change the system. And this enables real-world testing. We build the end-to-end system. You just need to plug in your optical hardware, and we can. This enables improvement of existing designs, evaluation, and also education. Okay, so how to build this? First, we have a generalized network architecture. Although there are many different architectures nowadays, we think many of them abstracted out as the layer of top-rack switches connected to the optical fabric. Well, of course, you can have host-based designs, but our work now is based on this TOR level abstraction. Okay, and the TORs are connected to the optical fabric, and we have some, we assume some optical circuit switches. They are connected in some structure depending on different optical architecture, and we can configure them throughout time. And the abstraction is actually called time flow table. This is similar to flow table. Like for the traditional SDN world, you have flows and each of them correspond to some entries in the flow table, and you can match them and define different behaviors. But in optical data center network, time is very important because the duration of a circuit lasts for some time, and this is essentially called a time slice. So we can define the time flow table like this. We add a field called arrival time slice and another field called the departure time slice. Okay, so we allow a packet to come into a switch at a particular time slice and to departure later. These can be the same time slice or different time slice, like shown here. So in the example above, the arrival time slice and departure time slice are the same, meaning the packet just like after it enters the switch, it just leaves, and you can match by the entry. And the second example is when it needs to be buffered and wait there for one time slice, and then it will departure. Okay. This abstraction is backward compatible to flow tables, like for some particular designs, like Google's Jupyter network. Your packet always leaves whenever it enters. So we just set the wildcard fields to these arrival and departure time slices. Okay, so here's the system overview. So on top, we have this management plane where we expose some user APIs, and the users can use some simple Python program to program the topology and routing. We can support a number of topologies and routings. And below is the fabric plane, where we can plug in different optical hardware, some emulated hardware, or even mininet, which we enable students to learn the principles of optical data center networks. Okay. And we have some monitoring functionalities, which goes back to the user, like showing the traffic, showing the queue utilization, bandwidth, packet loss, so on and so forth. Yeah, let's have a quick look at the user API. So we have three categories of user APIs. First is topology. So we can define what kind of optical connections you want. For example, the expander graph is basically a round robin kind of connectivity. So we have the most basic function called connect, which is like to connect the two ports of two top-of-rack switches. And those others are helper functions that are quite widely used by different routing mechanisms. For example, the round robin is just to rotate through different connections among the ports. Round robin offset is actually the Opera, the router net connection, where you can have different offsets to permutate different connections in your expander graph. And there are some like high dimensional round robin, which is recently proposed for even better connectivity. And we can have some routing functions, like the basic function routing, which takes a reference function called routing FN, which defines the paths, all the paths between a pair of ports. And after you push it into this routing wrapper, it will translate that into all the paths available in the network. Let's look at some example. Like this FN direct is to enable some like direct circuit routing, and we can implement VLB, Opera, or some later routing mechanisms. But each of them is to specify a number of paths for each top-of-rack switch pairs. And we have other enabler functions like neighbors, earliest paths, which is to find you the neighbors in one time slice and the earliest path between two nodes. These are to help you define some new routing protocols you want. And we can call entries to translate that into our time flow table entries, so the users don't need to program the low-level entries, and they just need to give the high-level incentives for the routing and topology, and everything can be translated automatically. And in the end, we have some monitoring APIs. Yeah, let's look at some examples. So you can define a network, okay? And here we can create a random topology, which is like we have a number of TORs. Each TOR has a number of ports, uplinks. So we just add them all to a list, and like one by one, we draw from the list so we can have random connections. And here's a routing function where we implement VLB. So VLB is a two-step routing where the packet is sent to all possible neighbors in the current time slice. And then after it arrives at this intermediate hop, then it needs to wait there until you have a direct connection to the final destination. So this example shows you how to program a functional network. Okay, then the implementation, like most of the implementation is in the switch. So the switch system mostly deals with packet buffering. Like remember for the time flow table, you may need to buffer the packet because it may leave the switch later. Let's see how that is done. So in this example, we have three paths. From TOR 1 to TOR 4, we have path 1 that the packet can leave TOR 1 at time slice 1 and then reach TOR 2. And then in time slice 2, it goes to TOR 4, so on and so forth. We have three paths. So these three paths correspond to three table entries in our time flow table. So we see if the packet comes in at time slice 2, then it will match to the second time slice, to the second table entry. So in our system, we leverage the latest feature of Tofino 2 switches, which is called queue pausing. It enables it allows a queue to be paused by an incoming packet, and you can unpause it later with another incoming packet. So in this way, we assign each queue a time slice. And every time there's only one active queue that actually drains traffic. This queue corresponds to the current time slice. And as time goes by, we can shift these queues one by one so that we that implements the path of time. Okay, so in this example, say one packet comes in at time slice 2, so it initially will match to the second entry in the time flow table. And we need to go through some initial control because for every time slice, you can only send a fixed number of bytes. So you need to see if this packet can fit into the current time slice. Say it cannot, if this queue is full already, then the packet will be recirculated and be matched to the next time slice because it can wait a bit longer and there might be other opportunities to send it in another path. And say this time is successful, so it will go to another queue, which is Q2, corresponding to time slice 4, which is 2 time slices later. Okay. Yeah, and we have done some optimization, which is to avoid packet recirculation, which is an expensive operation in programmable switches. Okay, so at first we wanted to build a completely in-network system on the switches, but we realized that's impossible. Still, some functionalities need to be on the host, especially because it is very, very expensive to pause some long flows, to store some long flows on the switches. So we have implemented this flow pausing functionality on the end host. So we detect adequate flows. And for those kind of flows, we only let it send when the circuit is ready so that we don't need to buffer a lot of packets on the switches. And on the host, we also have the back pressure functionality because when your network is congested, your congestion control mechanisms can deal with that on a certain degree, but you still need the last line of defense using flow control. So if it's overflowing your TORs, then you need to push back the traffic to the sender and telling it to stop sending. And we built the host system using the libVMA, which is a user space library. We use that because it has its own TCP UDP stack. So the user applications don't need to be changed at all. You can still use the legacy TCP UDP sockets. Okay, and we use a signal between the host and TORs to to notify the host when the circuits are ready. And we find the delay is quite short and also quite reliable. And that enables us to avoid actually synchronizing the host, but using explicit signals. Okay, and on our testbed, we can run different architectures on optical different optical architectures with their native routing, and we can have side-by-side performance comparisons. This is just one example. You can have many other use cases, like you can dive deeper into transport performance, and you can try out different applications, so on and so forth. Yeah. So this framework works as a research vehicle, which enables us to also do research on many other areas. Yeah. So for example, we have done time synchronization because this is actually an integral part of this framework, because to make it work, all the TORs need to be fully synchronized with the optical controller, and they need to know when the time has come, and like when your circuit is ready and when it is ready to set packets. And this work is under submission, and we have achieved a sync accuracy about like 20 to 30 nanoseconds for a 200 TOR cluster. And we have studied optical routing. There have been some routing work like Opera, but we find there still lacks principled research for routing, especially for multipath routing for optical data center networks. And Mai Jialong will give a presentation on the main conference on Wednesday. Yeah, we have published a work called UCMP, which is an ECMP equivalent for optical data center networks. And my student Federico is working on optical transport. He has a poster, so please check it out. Yeah, so I'll quickly, I think here I end the talk. Just some highlights of talks and events hosted by me and my group. So tomorrow there will be a non-paper session about SICOM reviewing Q&A. If you are curious about how SICOM papers are reviewed, please come join our discussion. Okay, and on the 6th, Jialong will give a talk about this UCMP routing. And for the poster and demo, Yiming will give a demonstration of this open framework. And if you are curious, you can download the code and play with it. And Federico will give a poster presentation about some transport work for optical DCS. Okay, that's all.
Any questions? We can have 1 or 2 questions.
So the control plane, it looks like you're emitting packets from the TOR based off of paused packets that are being sent from the individual hosts. Is that correct?
So
where are the paused packets coming from?
Oh, the packet, the pausing is from, so there are different types of routing. Okay, so if you use Opera routing, you won't pause traffic. But there are other types of routing, such as VLB or like this new routing Jialong has proposed. So for some routing, it allows packets to wait at an intermediate TOR and to be sent out in a later time slice. And we find that this end-to-end will give you lower latency. So this pausing comes from that type of routing. And because we are building a general framework, we need to support all sorts of different routing mechanisms.
Okay, I guess I missed it. So the switch itself has to be synchronous with the TORs on the uplinks, right? Because you've got to be able to send the packets out when the switch is ready. But that the paused packets don't do that. How is the optical switch coordinated with the TORs, plural? And is that coordination centralized across all the TORs in the network?
Yeah, so yeah, the short answer is we don't explicitly synchronize hosts, but we rely on the signal messages like from the TORs. to notify the host when the circuits are ready. That is because we have done some measurements. We find the delay is quite minimal, especially it's very reliable. Like the variance is very small. So how the system works is we synchronize TORs, okay? And for short mice flows, we just let them to be set. And if they need to be paused, they will be stored on the top rack switches. And what we find, they have enough memory for that. But for elephant flows, we cannot afford that. We have to pause the flows at the end host and resume it only when the circuits are ready. And that is based on the signals from the TORs. Did that answer your question?
I'm just missing the synchronization of either the optical switch is synchronized with the TORs.
With the
or
TORs.
synchronized with the host. And then you have shallow queues, so you don't have any queuing delay between the TORs. So what's the fundamental synchronization mechanism of the optical switch? Is it both with the TORs and the end host?
No, only with the TORs. So only TORs are synchronized with the optical controller, and the host gets control messages from the connected TOR.
Okay, so then that I got. So, but is that synchronization then across all of the TORs that are connected to a single optical switch?
Yes.
Okay.